Hello, this is Math 2270 from the College of DuPage for summer 2020. This is our lecture called Riccati Equation. Last time I left you working on this problem. I hope you were able to complete it, but if not, or if you didn't try it yet, you know what to do. Let's see how you did. Now this time the constant c of x, the c of x function is not a constant, so it is more complicated. And what we're going to do is we're going to guess a solution. Now if you think about this for a while, you could say, oh, I'm taking the derivative of something and I'm squaring something, so that motivates you to think for a particular solution of the form y is equal to c over x, which would mean y prime is equal to minus c over x. If we substitute this into the differential equation, we obtain this expression, which can be simplified this way. In order for this to be true, the numerator would have to be true if you move this to the other side, and so we have a quadratic equation for c that we would have to solve. So this can be a solution when c is either minus 1 or 2. We're going to take any value of c, either minus 1 or 2, but let's take 2 so they don't have to deal with a minus sign. Okay, so now what we're going to say is this solution of 2 over x added to the general solution is a solution of the Riccati equation. And if this is what y is, this is what y prime is. Again, we're taking the derivative with respect to x. So we're going to substitute these into the original equation. And so we will get this, and as promised by the theorem that we studied, the annoying factor will cancel out, and we're left with just a Bernoulli equation with a parameter of minus 2. So we can make this substitution that we learned in the Bernoulli equation to change this into a linear equation. And the linear equation is going to be this one. Now, we have to be careful because there's a minus sitting there, but it will all be good. So that means we can find the integrating factor for that, and we get this as an integrating factor, and we multiply all the way through and solve that linear equation to get this for what v is. I encourage you to do all of these steps and make sure you can do this, because you are an engineer. You will be required to do this kind of work. And now we know what v is, so we can invert the first substitution from the Bernoulli. Actually, it was a second substitution, I suppose. This was a substitution we were using with the Bernoulli, so that means that what we get for z is going to be this. But then y was z plus our original assumed solution. We do the calculation and we get these expressions upon simplification. And we play a little bit loose with our constants, renaming them and so on and so forth. We can get this is the general solution. Neat, huh? Let's look at another example. So here we're to find the general solution of this differential equation. Again, you want to come up with a trial solution that you can work. So you want to think about the structure of this as well. Let's see how you do. Let's see how you did. Well, we can convert this equation this way, and you can see, oh, it is a Riccati equation. But you see, it didn't. We get a different thing, and so the offensive function is this one. And as we think about that, we're motivated by the structure of this differential equation to try something that is the form y1 is equal to cx squared. We substitute this into the Riccati equation, this one, and we determine the coefficients of c. And again, you see we picked it so that we have matching powers of x at the end of the day. So what we get is this expression, which means this is the quadratic that we have to solve. And if I rearrange it as a quadratic, it's this. Now I can use the quadratic formula or factor. Actually, this time I guess I have to, well, either way. So I will get that c either is 1 or 2. I could choose either one, and in fact 1 is simpler than 2, so we're going to use 1. So we just say, oh, our particular solution is y1 is equal to x squared. So what we can do is then, as we do with the theorem, we say y is equal to x squared plus u, and we substitute it in, and as the theorem works, it allows us to eliminate this 2x. That will cancel one with another, and what we end up with at the end of the, not at the end of the day, but the next step, we end up with a Bernoulli equation then. And so we can solve this. Now we're engineers, so we really have to solve this. So we make the Bernoulli substitution. Z is equal to 1 over u, converting it to a linear differential equation. Again, we have to look at all of these elements of the solution. So this is the linear differential equation that we're going to be solving, is this one in Z. We have to calculate an integrating factor this way, and we multiply all the way through by the integrating factor, and you can certainly check that. And so once you do the integrating factor and solve, what you get is that this is the solution for Z. Z is equal to this. You should check all of these steps. But Z was 1 over u, and so u is 1 over z, and so this is what we get. So the general solution of the original Riccati equation is given by, I add the solution that we guessed, plus the one that we found here, and simplify, and we get that y is equal to this is the general solution, where c is a constant. Here's one more example, again a little bit more complex function for c of x. You know what to do. Let's see how you do. Okay, so we do a substitution of y is equal to 1 over z, and we do the work, and we change this into a homogeneous differential equation. Notice it's homogeneous of degree 0 because that what we have there. And then we have a homogeneous equation. We know how to solve it. This is good review. We take z to be t times x, and that means that z prime is equal to this. And we can then separate variables after we make that substitution. And we separate the variables, and now we have a differential equation in x and t. Again, t is z over x. And so we have separated variables here now. Well, this can be factored, and so we realize the way we're going to do this integral is going to be by partial fraction decomposition. So the trinomial there can be factored this way, and so we can use partial fraction decomposition, determining what a and b have to be, and we figure out that a has to be minus 1/5 and b has to be 1/5. Make sure you can do these steps because you will have to do these to solve the problems. So we integrate, and we get here, using properties of logarithms, this is the logarithm of the, this is the difference of the logarithms, which is the logarithm of the quotient. You get this, and we now have a constant c1, and c1 has to be bigger than 0. So we have the logarithm of this business is the logarithm of this business. That means we can exponentiate both sides, and we get this. And that tells us that we have this must be true. And again, you see we've got plus or minus, but we can just call that a c. So the solution t of x will be of this form. Again, we're just using this, renaming c. But remember that z over x was equal to t, so we can substitute back in for that. And we get this is our expression in z and x. But now we have to return to the variable y, which was z was equal to 1 over y. We substitute that in, and we get this expression. So that is the general solution for the Riccati equation in implicit form. Now, since c was any real number, if we took c to be 0, we could say, oh, here is a solution. Let's see, if we take c to be 0, that we could have an expression there, and we would have to solve that. But what we would get is that y was equal to minus 1 over 3x. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other.